So for this part, we're going to be adding energy, which does not change temperatures for phase diagrams. So let's go ahead and talk about what happens when you add heat to a phase diagram or to different phases of matter. So in this example, we're going to increase the kinetic energy, which generally is going to increase temperature if you're adding heat. However, these are going to be governed by specifically phase changes. So there's going to be something that could be used to be calculating that out. Now, in order to break the intermolecular bonds, which have no effect on average speed, this is often called latent heat or hidden heat due to the fact that there's no obvious effect on temperature. So in order to break the IMF bonds from a solid to a liquid, and you're providing that energy in, the temperature will not change. And what we're trying to see right here is why is that the case is because all that energy is being used to break those IMF bonds. So that goes for melting and that also goes for liquid to a gas. And what's very important about this is to understand that temperature is going to be a function of energy. So when you're looking at Q equals MCAT, you want to be able to calculate that temperature change when you have a positive slope. So that's because the temperature is changing where we can use that. However, in order to take a look at heat or phase transitions, we notice carefully there's no change in temperature, so we cannot use Q equals MCAT. And the reason why is because there is no change. So the way we're going to do that is we're going to have to take into account the amount of heat that's being applied during phase changes. So keep in mind a couple of things. The potential energy is changing as the molecules are changing phases. In addition to that, we are actually disrupting IMF. So let's go ahead and review quickly about what phase changes are. So when I go from a liquid to a solid, we're going to be freezing, or it's called solidification. So in other words, when I go from here to a liquid, we're going to be freezing. When we're melting, we're going to call this one fusion. So that goes from a solid to a liquid. And the word fusion pretty much is going to be governing our delta H's, evaporations from a liquid to a gas, condensations from a gas to a liquid, and sublimations from a solid to a gas. Deposition is a little bit different. It's actually the reverse. We're going from a gas to a solid. And based off of these phase changes, you're going to have different parts of the curve that are going to be labeled as such. So going over from the solid, you're going to have a solid from this point right here to the melting and freezing. And to the liquid, it's going to be vaporizing and condensing. Sorry. So let's talk about what these delta values are going to be. So melting, we're going to call it delta H of fusion. And vaporization is called delta H of vaporization. So the molar enthalpy of fusion, or called delta H fusion, is the amount of heat absorbed by 1 mole of a solid as it melts to a liquid constant temperature. So this is going to be how much you're going to be adding in to melt and go from a solid to a liquid. The molar enthalpy of vaporization is going to be the amount of heat that's being absorbed to vaporize that liquid. So we're going to be abbreviating that as delta H VAP. Now, keep a couple of things note. The molar heat of vaporization is larger than the molar heat of fusion because it's going to take more energy to completely separate the molecules to form a gas. So think about it from the perspective of the molecule. In order to make it into a gas, you're going to need a lot of energy to go from a liquid to a gas. And the enthalpy changes for the reverse phases are always negative. So they're still going to be the same number, except that these values are always going to be a minus instead. Okay, so let's go back and talk about what these delta H's is. So delta H solidification equals negative H of fusion. Delta H of condensation equals negative H of vaporization. So as you can see from here, you're going to get negative values for each one as you're going backwards. So to calculate a Q during phase changes, you generally are going to be using Q equals N delta H, where N refers to the molar heat. And we're going to go ahead and report these so that we can calculate the molar enthalpy. Now keep in mind it's also possible for delta H to be reported as kJ per mole. Sometimes it's going to be kJ per mole or kJ per G. In that case, you would actually multiply delta H by mass instead of moles. So delta H can also be reported as cal G or cal mole, where the units of energy are calories instead of joules. Always note your units and make sure you know your units for your guide. Okay, go ahead and pause the video to complete these calculations, and we're going to go ahead and go over these in the class.